The universe is a place of endless wonder, stretching across distances so vast they defy imagination. Yet, what lies beyond the edges of what we can see? What forces drive its unrelenting expansion? Today, we embark on a journey through 30 of the most fascinating theories that attempt to unravel the mysteries of the universe's infinite growth. From the explosive birth of the cosmos in the Big Bang to the mind-bending possibilities of the multiverse, each theory offers a unique lens through which we can glimpse the secrets of existence. As we explore these ideas, you'll discover how scientists, philosophers, and dreamers alike have wrestled with one of the greatest questions of all. How does the universe expand, and what does it mean for everything we know? Stay with us, because by the end of this exploration, you'll not only have a deeper understanding of the cosmos, but also a renewed sense of awe for the boundless mysteries that surround us. Let's dive in. Now, turning to the foundation of modern cosmology, we begin with the Big Bang theory. This theory suggests that the universe erupted into existence from an incredibly hot, dense state around 13.8 billion years ago. In its earliest moments, the universe was smaller than a single atom, but it has been expanding ever since. This idea of infinite expansion stems from the observation that galaxies are moving away from each other, a concept first solidified by Hubble's law. Edwin Hubble discovered that the farther a galaxy is from us, the faster it appears to be receding. This was a groundbreaking revelation, as it implied that the universe itself is stretching. Another key piece of evidence supporting the Big Bang is the cosmic microwave background radiation, a faint glow of energy that permeates the universe. This radiation is essentially the afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. Together, these discoveries paint a picture of a universe that began with a colossal explosion and has been expanding ever since, setting the stage for all the theories that follow. Now, shifting our gaze to the moments immediately following the Big Bang, we encounter the fascinating concept of cosmic inflation. This theory proposes that in the tiniest fraction of a second after the universe's birth, it underwent an extraordinary period of exponential expansion. Imagine the universe stretching faster than the speed of light, growing from something smaller than a proton to the size of a marble in less than a blink of an eye. This rapid inflation didn't just make the universe bigger, it also smoothed out its irregularities, explaining why the cosmos appears so uniform on a large scale today. Without this process, the universe might have been riddled with clumps and inconsistencies, making the structure we observe now nearly impossible. But cosmic inflation's significance doesn't stop there. It also provides a framework for understanding the seeds of cosmic structures like galaxies and galaxy clusters. Tiny quantum fluctuations during this inflationary period were stretched to cosmic scales, eventually becoming the gravitational wells that pulled matter together to form the large-scale structures we see today. This theory isn't just a footnote in the history of the universe. It's a cornerstone of our understanding of how the cosmos evolved from its infancy to the vast, ever-expanding expanse we inhabit now. So, when we look at the universe today, we're essentially seeing the long-term effects of that brief but monumental burst of growth. With this in mind, cosmic inflation not only connects the dots between the Big Bang and the universe's current state, but also raises profound questions about the nature of space, time, and the very fabric of reality itself. Now, pivoting to one of the most mysterious forces shaping our universe, we delve into the enigmatic concept of dark energy. Unlike anything we can see or touch, dark energy is the invisible force driving the accelerated expansion of the universe. Back in the late 1990s, astronomers made a startling discovery while observing distant supernovae. They found that the universe isn't just expanding, it's expanding faster and faster over time. This revelation was so unexpected that it turned our understanding of cosmology on its head. Dark energy is the term used to describe whatever is causing this acceleration, and it makes up roughly 68% of the universe's total energy content. But what exactly is it? The truth is, we don't fully know. Some theories suggest it's a property of space itself, often referred to as the cosmological constant, while others propose it could be a new kind of field or energy that permeates the cosmos. What makes dark energy so perplexing is how it defies our fundamental understanding of gravity. According to Einstein's theory of general relativity, gravity should be pulling the universe together, slowing its expansion. Instead, dark energy seems to act as a kind of anti-gravity, pushing the universe apart. This raises profound questions about the ultimate fate of the cosmos. If dark energy continues to dominate, the universe could keep expanding forever, eventually leading to a cold, dark, and lonely end, a scenario known as the Big Freeze. But there are even more dramatic possibilities. Some models suggest that dark energy could grow stronger over time, tearing apart galaxies, stars, and even atoms in a catastrophic event called the Big Rip. As we grapple with these ideas, dark energy remains one of the greatest puzzles in modern science, challenging us to rethink not just the universe's expansion, but the very nature of reality itself. Now shifting our gaze beyond the boundaries of our own universe, we explore the fascinating idea of the multiverse theory. This concept suggests that our universe might not be the only one. Instead, there could be countless other universes, each with its own unique set of physical laws and constants, expanding endlessly alongside ours. The multiverse theory isn't just science fiction. It's rooted in rigorous scientific frameworks like quantum mechanics and string theory. In quantum mechanics, every possible outcome of a situation is thought to exist in its own separate universe, creating a vast web of parallel realities. String theory, on the other hand, proposes that our universe is just one of many membranes or branes, floating in a higher dimensional space, with each brane representing a distinct universe. These ideas challenge our understanding of reality, suggesting that what we see as the universe might be just one tiny piece of a much grander cosmic puzzle. The implications are staggering. If the multiverse exists, it could explain why our universe seems so finely tuned for life. Perhaps in the endless sea of universes, ours is simply the one where the conditions happen to be just right. Yet, despite its compelling nature, the multiverse theory remains speculative, as it's incredibly difficult to test or observe these other universes directly. Nonetheless, it opens up a universe of possibilities, literally pushing the boundaries of our imagination and inviting us to rethink everything we thought we knew about existence. Now expanding our perspective beyond the multiverse, let's delve into the holographic principle, a theory that challenges our understanding of the very fabric of reality. This intriguing idea suggests that the entire universe, with all its three-dimensional complexity, might actually be a projection from a two-dimensional surface. Think of it like a hologram, where a flat image creates the illusion of depth and dimension. According to this principle, all the information about the universe's expansion, its contents, and even the laws of physics could be encoded on a two-dimensional boundary, much like a cosmic movie screen. This concept stems from the study of black holes, where physicists discovered that the information about objects falling into a black hole is preserved on its event horizon, a two-dimensional surface. The holographic principle takes this idea further, proposing that our entire universe might operate in a similar way. If true, this would mean that what we perceive as three-dimensional space and its infinite expansion could be a kind of illusion, a holographic projection from a simpler, lower-dimensional reality. It's a mind-bending concept that not only reshapes our understanding of space and time, but also raises profound questions about the nature of existence itself. Could the universe's expansion be a kind of cosmic hologram, unfolding from a hidden two-dimensional code? While this theory remains speculative, it offers a radical new lens through which to view the mysteries of the cosmos, inviting us to rethink the very foundations of reality. Now shifting our focus to another groundbreaking theory, let's explore the Ekpyrotic Universe. This concept offers a fascinating alternative to the Big Bang, suggesting that the universe's expansion might have been triggered by the collision of multi-dimensional structures known as branes. In this theory, our universe exists on one of these branes, which floats in a higher dimensional space. The idea is that when two branes collide, the energy from that collision sets off the rapid expansion of our universe, much like the aftermath of a cosmic crash. Unlike the Big Bang, which implies a singular starting point, the Ekpyrotic Universe proposes that such collisions could happen repeatedly, creating a cycle of expansion and contraction. This theory helps explain some of the mysteries the Big Bang struggles with, such as why the universe appears so uniform in all directions. By suggesting that the universe was stretched and smoothed out during these brane collisions, the Ekpyrotic Universe provides a compelling alternative to the traditional narrative. While it's still a speculative idea, it opens up exciting possibilities for understanding the origins and expansion of our cosmos. Could our universe be just one episode in an endless series of brane collisions? This theory invites us to rethink the very nature of cosmic beginnings, offering a fresh perspective on the mysteries of existence. Now turning to another intriguing perspective, let's consider the cyclic model of the universe. This theory proposes that our cosmos is caught in an endless loop of expansion and contraction, with no true beginning or end. Imagine the universe as a cosmic accordion, stretching out and then folding back in on itself over immense periods of time. According to this model, the Big Bang wasn't a one-time event but rather one phase in an infinite series of expansions followed by contractions, often referred to as the Big Crunch. During the expansion phase, galaxies drift apart and space grows larger, much like what we observe today. However, instead of continuing to expand forever, gravity eventually takes over, pulling everything back together in a dramatic collapse. This process repeats itself, creating a universe that is constantly reborn. The cyclic model addresses some of the questions left unanswered by the Big Bang, such as what came before it, by suggesting there was no before, just an eternal cycle of change. While this idea is still theoretical, it offers a fascinating alternative to the idea of a singular cosmic origin, inviting us to rethink the universe as a timeless, ever-evolving entity. Could our universe be just one chapter in an infinite cosmic saga? This theory challenges us to view existence not as a linear story, but as a never-ending dance of creation and destruction. Now shifting our gaze to another perspective, let's explore the steady-state theory, a once popular idea that challenged the notion of an endlessly expanding universe. Unlike the Big Bang or cyclic models, the steady-state theory suggests that the universe has always existed and will continue to exist in a constant, unchanging state. According to this theory, as the universe expands, new matter is continuously created to fill the gaps, ensuring that the overall density of the cosmos remains the same over time. This idea of continuous creation was proposed as a way to explain why the universe appears uniform on a large scale, without the need for a singular explosive beginning or cycles of collapse. The steady-state theory was supported by observations of the universe's large-scale structure, which seemed to align with its predictions of a balanced, eternal cosmos. However, as scientific evidence accumulated, particularly the discovery of the cosmic microwave background radiation, the theory began to lose its footing. This radiation, a faint echo of the Big Bang, provided strong evidence for an expanding universe with a definite beginning, contradicting the steady-state's claim of no starting point. Despite being largely discredited, the theory remains an important part of cosmological history. It reminds us of the creativity and boldness required to question established ideas, even when they eventually give way to new understandings. So, while the steady-state theory may no longer hold sway in modern cosmology, its legacy lives on as a testament to the ever-evolving quest to understand the universe. Could it still hold a grain of truth waiting to be rediscovered in some future revelation? This theory invites us to reflect on how our understanding of the cosmos is shaped by the evidence we uncover and the ideas we dare to imagine. Now turning to a fascinating alternative perspective, let's delve into the bouncing universe theory. This intriguing concept suggests that the universe doesn't just expand endlessly or collapse into nothingness, but instead goes through an infinite cycle of expansion and contraction, a cosmic bounce. Imagine the universe as a massive spring, stretching out and then pulling back in over and over again. According to this theory, the current expansion phase we observe might one day slow down, reverse, and lead to a contraction, culminating in a big crunch. But instead of ending there, the universe would rebound, initiating a new Big Bang and starting the cycle all over again. This idea offers a solution to the question of what might have existed before the Big Bang, proposing that our universe is simply the latest iteration in an endless series of cosmic rebirths. While the theory is still speculative, it's supported by certain interpretations of quantum mechanics and general relativity, which suggest that the conditions of a collapsing universe could naturally lead to a bounce rather than a singular endpoint. The bouncing universe theory also raises profound questions about the nature of time, space, and existence itself. Could the universe be eternal, not in a static sense, but through an infinite dance of creation and destruction? This theory challenges us to think beyond linear models of cosmic history and consider the possibility that the universe operates in cycles, each one bringing new possibilities and mysteries. While the evidence for this idea remains inconclusive, it continues to inspire researchers and spark curiosity about the deeper rhythms of the cosmos. Could the universe's expansion be just one phase in a grander, never-ending cycle? The bouncing universe theory invites us to ponder this captivating possibility. Now shifting our gaze to a more unsettling possibility, let's explore the phantom energy hypothesis. This theory introduces a concept called phantom energy, a speculative form of dark energy with a truly terrifying implication: the Big Rip. Unlike other theories that envision the universe's expansion slowing down or reversing, phantom energy suggests the opposite. It proposes that the expansion of the universe could accelerate to such extreme speeds that it would eventually tear everything apart. Picture this: galaxies, stars, planets, even atoms and subatomic particles, all ripped asunder by the relentless force of expansion. The Big Rip would mark the ultimate end, not with a whimper, but with a catastrophic shredding of the very fabric of existence. This hypothesis hinges on the idea that phantom energy's density increases over time, creating an ever-expanding force that overwhelms all other cosmic interactions. What makes this theory particularly chilling is that it doesn't just predict the end of life, it predicts the end of matter itself. While it's still a speculative idea, the phantom energy hypothesis forces us to confront the possibility that the universe's expansion could ultimately lead to its complete disintegration. It challenges our understanding of dark energy and raises profound questions about the ultimate fate of the cosmos. Could the universe's expansion, which we often celebrate as a sign of its vibrancy, actually be its undoing? The phantom energy hypothesis invites us to grapple with this haunting vision of cosmic destruction. Now venturing into another profound and unsettling concept, let's examine the vacuum decay theory. This idea revolves around the notion that our universe might not be in its most stable state. Imagine the universe as a bubble in a vast cosmic foam. What if this bubble popped? Vacuum decay suggests that the universe exists in a false vacuum, a seemingly stable but not entirely secure state. If the universe were to transition into a true vacuum, a lower energy state, it could trigger a catastrophic event. This transition would propagate outward at the speed of light, fundamentally altering the laws of physics as we know them. Picture this: one moment, the universe operates under the familiar rules that govern stars, planets, and life itself. The next moment, those rules dissolve, replaced by a new set of physical laws. The result, everything, galaxies, solar systems, atoms, would be destroyed in an instant. The vacuum decay theory is especially chilling because it could happen at any moment without warning. Unlike gradual cosmic processes, this event would be sudden and irreversible. While it remains a speculative idea, it challenges our understanding of the universe's stability and raises a haunting question: could the very fabric of reality be hanging by a thread? This theory invites us to consider the fragility of the cosmos and the possibility that its expansion could one day lead to its abrupt and total annihilation. Now, shifting our focus to the tiniest building blocks of the cosmos, let's explore the quantum foam theory. At the smallest scales imaginable, the fabric of spacetime isn't smooth and continuous, but instead resembles a frothy, bubbling foam. This quantum foam is a chaotic sea of fluctuations where particles and antiparticles pop in and out of existence in fractions of a second. These fleeting disturbances might seem insignificant, but they could have profound implications for the universe's expansion on the grandest scales. The quantum foam theory suggests that these microscopic fluctuations could influence the behavior of spacetime itself, potentially driving the large-scale expansion we observe. Think of it like ripples on the surface of a pond. What starts as a tiny disturbance can spread and grow, affecting the entire body of water. In the same way, the unpredictable churn of quantum foam might create ripples in spacetime that ripple outward, contributing to the universe's accelerating expansion. This idea bridges the gap between quantum mechanics and cosmology, suggesting that the universe's largest structures and behaviors are shaped by its smallest and most fleeting phenomena. While it's still a highly theoretical concept, the quantum foam theory challenges us to think about how the tiniest scales of existence might hold the key to understanding the grandest mysteries of the cosmos. Now, turning to a theory that unifies some of the most profound ideas in physics, let's dive into M-theory. Imagine the universe not as the three-dimensional space we see, but as a realm with 11 dimensions. M-theory suggests that our observable universe is just one part of a much larger, multidimensional reality. At its core, M-theory attempts to bring together the principles of string theory, which describes particles as tiny vibrating strings, with the concept of brane. Branes are multidimensional objects that can exist in these higher dimensions. In this framework, our universe could be a three-dimensional brane floating within a higher dimensional space. The expansion of the universe in this model might be influenced by interactions between branes in these extra dimensions. Picture it like sheets of paper floating in a vast, unseen ocean, each sheet representing a universe and their movements and collisions shaping the cosmos. M-theory proposes that the universe's expansion isn't just a random occurrence, but could be the result of these higher dimensional dynamics. While still a work in progress, M-theory offers a fascinating perspective on how the universe's expansion might be tied to dimensions beyond our perception. It challenges us to rethink our understanding of reality, suggesting that the answers to some of the universe's biggest mysteries might lie in dimensions we can't yet see. Now, shifting our focus to a groundbreaking approach that reimagines the very fabric of the cosmos, let's explore the loop quantum gravity theory. Unlike traditional models of gravity, which rely on smooth, continuous spacetime, loop quantum gravity introduces the idea that spacetime itself is made up of tiny, discrete loops. Imagine spacetime as a finely woven fabric where each thread represents a quantum loop. These loops are the smallest possible units of space and time, creating a granular structure at the universe's most fundamental level. In this framework, the expansion of the universe isn't a smooth, continuous process, but rather a series of quantum jumps. Picture it like a movie made of individual frames. Each frame represents a quantum state of spacetime, and the transitions between frames create the illusion of smooth motion. Loop quantum gravity suggests that the universe's expansion could be the result of these quantum transitions, offering a completely new way to understand how the cosmos grows. This theory also avoids the singularities found in classical physics, such as the infinitely dense point at the Big Bang, by proposing that space-time loops prevent such extremes. While still a developing field, loop quantum gravity challenges our conventional understanding of space-time and provides a fresh lens through which to view the universe's expansion. It invites us to consider that the cosmos might be built not on smooth, unbroken fields, but on a tapestry of interconnected quantum loops. Now turning to a theory that harmonizes the microscopic with the cosmic, let's unravel the fascinating concept of string gas cosmology. This theory builds on the idea that the fundamental building blocks of the universe are not point-like particles but tiny, vibrating strings. In the early universe, these strings wove together to form a dense, chaotic gas. As the universe expanded, the behavior of these strings dictated the dynamics of cosmic growth. Picture the early cosmos as a bustling marketplace where strings collided, vibrated, and interacted with one another. These interactions generated energy and momentum, driving the universe's expansion in a way that's fundamentally different from traditional models. String gas cosmology suggests that the universe's initial rapid expansion, known as inflation, might have been fueled by the collective behavior of these strings. Unlike other theories which rely on external fields or forces, this model proposes that the strings themselves were the architects of cosmic expansion. What's even more intriguing is that this theory naturally explains the large-scale structure of the universe. The patterns we observe in galaxies and galaxy clusters could be the remnants of these early string interactions. While still a theoretical framework, string gas cosmology offers a compelling narrative that ties the universe's expansion to the fundamental nature of matter itself. It invites us to imagine a cosmos where the tiniest threads of existence played a pivotal role in shaping the vast expanse we see today. Now shifting our perspective to a theory that merges two profound ideas, let's explore the holographic inflation theory. This concept combines the principles of holography and cosmic inflation, suggesting that the universe's expansion could be encoded in a lower dimensional space. Imagine the universe as a vast, intricate hologram, where all the information about its three-dimensional structure is stored on a two-dimensional surface. This idea stems from the holographic principle, which posits that the information in a region of space can be represented as residing on its boundary. When applied to cosmic inflation, this theory proposes that the rapid expansion of the early universe might have been governed by the dynamics of this lower dimensional surface. In simpler terms, the three-dimensional universe we observe could be a projection from a two-dimensional code. This idea challenges our traditional understanding of space and its dimensions, offering a radical new way to think about the cosmos. The holographic inflation theory not only provides a novel explanation for the universe's expansion, but also bridges the gap between quantum mechanics and general relativity. It suggests that the patterns we see in the universe's large-scale structure, such as the distribution of galaxies, might be a direct result of this encoding process. While still theoretical, this model invites us to reconsider the very nature of space and time, envisioning a universe where the vast and the microscopic are deeply interconnected. It's a compelling narrative that pushes the boundaries of our cosmic understanding, blending the abstract with the observable in a way that continues to intrigue scientists and enthusiasts alike. Now turning to a fascinating idea that blends thermodynamics with cosmology, let's explore the entropic gravity theory. This concept proposes that the universe's expansion might be driven by entropy, the measure of disorder or randomness in a system. According to this theory, gravity itself could emerge as an entropic force, a byproduct of the universe's tendency to maximize entropy. Imagine the cosmos as a vast, ever-evolving system where the flow of information and energy shapes the very fabric of reality. In this view, the expansion of the universe isn't just a result of dark energy or cosmic inflation, but is deeply tied to the fundamental principles of thermodynamics. The entropic gravity theory suggests that as the universe expands, it naturally increases its entropy, creating a kind of cosmic tension that drives galaxies apart. This idea turns our traditional understanding of gravity on its head, painting it not as a fundamental force but as an emergent phenomenon arising from the behavior of information at the largest scales. While still a theoretical framework, entropic gravity offers a compelling way to unify quantum mechanics and general relativity by focusing on the role of information in shaping the cosmos. It invites us to rethink the nature of gravity itself, viewing it not as a force but as a consequence of the universe's inherent drive toward disorder. This theory opens up new avenues for understanding the universe's expansion, blending the abstract with the observable in a way that continues to challenge and inspire our cosmic curiosity. Shifting our focus to a concept that tests the boundaries of physics, let's examine the null energy condition. This principle, rooted in the study of space-time and energy, plays a crucial role in our understanding of the universe's expansion. The null energy condition asserts that certain types of energy density cannot be negative, imposing constraints on how matter and energy behave in the cosmos. At its core, it challenges the idea that exotic forms of energy could drive the universe's acceleration without violating fundamental physical laws. This condition is particularly significant when considering the behavior of dark energy, the mysterious force responsible for the universe's accelerating expansion. If the null energy condition holds true, it implies that dark energy must adhere to specific rules, limiting the possibilities for how it operates. However, some theories, such as those involving phantom energy, propose scenarios where this condition might be violated, leading to dramatic outcomes like the Big Rip, where the universe's expansion tears apart galaxies, stars, and even atoms. The null energy condition forces us to confront the delicate balance between observation and theory, pushing us to refine our models of the cosmos. It raises profound questions about the nature of energy and the limits of our physical understanding. By examining this condition, we gain deeper insight into the mechanisms driving the universe's expansion and the challenges that lie ahead in unraveling its mysteries. This theory invites us to explore the interplay between energy, gravity, and the fabric of space-time, reminding us that the cosmos is far more complex than we often imagine. Now, shifting our gaze to a theory that stretches the imagination, let's delve into the eternal inflation theory. This intriguing concept suggests that the universe isn't just expanding, it's doing so endlessly in different regions, giving rise to a multiverse. Eternal inflation builds on the idea of cosmic inflation, which describes the rapid expansion of the universe moments after the Big Bang. However, while cosmic inflation is thought to have occurred in a brief, explosive phase, eternal inflation proposes that this process never truly stops. Instead, certain regions of the universe continue to expand exponentially, creating bubbles of space that each evolve into their own separate universes. These bubble universes can have different physical laws, constants, and even dimensions, making the multiverse a vast and diverse landscape. What's fascinating is that this theory isn't just speculation, it's supported by mathematical models that align with our observations of the cosmos. For instance, the uniformity of the cosmic microwave background radiation can be explained by the idea that our observable universe is just one of many bubbles in a larger, eternally inflating space. Eternal inflation also raises profound questions about the nature of reality. If an infinite number of universes exist, each with its own unique properties, what does that mean for our understanding of existence? Could there be other versions of us in these parallel worlds, living out different possibilities? While the theory remains unproven, it offers a compelling framework for thinking about the universe's infinite expansion and the potential for countless other realities beyond our own. By exploring eternal inflation, we're invited to consider not just the vastness of our universe, but the limitless possibilities that lie beyond it. Now, guiding our attention to a theory that challenges one of the most fundamental constants in physics, let's explore the variable speed of light theory. This groundbreaking idea suggests that the speed of light, which we've long considered an unchanging law of nature, might not have always been constant. In fact, it's theorized that the speed of light could have been significantly different in the early universe, playing a crucial role in its expansion. According to this theory, a faster speed of light in the universe's infancy would have allowed energy and information to travel much more quickly, potentially explaining how the universe grew so large so rapidly in its early stages. This concept also provides an alternative explanation for certain phenomena, such as the uniformity of the cosmic microwave background radiation, without relying solely on the idea of cosmic inflation. If light traveled faster in the past, it could have smoothed out temperature fluctuations across vast distances, creating the even distribution of radiation we observe today. The variable speed of light theory doesn't just challenge our understanding of physics, it opens up new possibilities for explaining the universe's expansion. Could other physical constants have also varied over time? And if so, how might that reshape our understanding of the cosmos? While this theory remains speculative, it encourages us to question the very foundations of our knowledge and consider how the universe's history might be far more dynamic and complex than we've imagined. By examining the variable speed of light, we're reminded that even the most fundamental laws of physics might have hidden layers waiting to be uncovered. Now, shifting our gaze to another compelling idea, let's delve into the modified gravity theory. This concept challenges the conventional understanding of gravity as defined by Einstein's general relativity, suggesting that our current framework might not fully explain the universe's accelerating expansion. Instead of attributing this expansion to dark energy, modified gravity theories propose that gravity itself behaves differently on cosmic scales. One of the most well-known examples is modified Newtonian dynamics, or MND, which alters the laws of gravity to account for observed motions of galaxies without invoking dark matter or dark energy. These theories suggest that at extremely large distances, gravity weakens or behaves in ways we don't yet fully understand, potentially explaining why galaxies and cosmic structures appear to be moving apart faster than expected. Modified gravity theories also offer alternative explanations for phenomena like the rotation curves of galaxies, which seem to defy predictions based on visible matter alone. While these ideas are still being tested and debated, they open up exciting possibilities for rethinking one of the most fundamental forces in the universe. Could gravity itself hold the key to understanding cosmic expansion? And if so, what would that mean for our broader understanding of the cosmos? By exploring modified gravity, we're reminded that even the most established laws of physics are open to reinterpretation, inviting us to question and refine our understanding of the universe's grand design. Now, stepping into the realm of the unseen, let's explore the cosmic neutrino background and its potential role in shaping the universe's expansion. Neutrinos, often called ghost particles, are incredibly elusive subatomic particles that barely interact with matter, yet they are everywhere. Billions of them pass through your body every second without you ever noticing. These particles were produced in massive quantities during the early moments of the universe, just fractions of a second after the Big Bang. Today, they form what's known as the cosmic neutrino background, a faint remnant of that explosive beginning. But how do these ghostly particles influence the universe's expansion? Cosmic neutrinos, though nearly massless, have a cumulative effect on the cosmos. As they move at nearly the speed of light, they contribute to the overall energy density of the universe, subtly affecting its rate of expansion. On a larger scale, their presence can also influence the formation of cosmic structures like galaxies and galaxy clusters. By studying the cosmic neutrino background, scientists can gain insights into how these particles shape the universe's large-scale architecture. Interestingly, neutrinos might also play a role in solving some of the mysteries surrounding dark matter and dark energy, as their behavior could offer clues to the forces driving cosmic expansion. Are these ghost particles quietly holding the key to understanding the universe's grand design? As we continue to unravel the mysteries of the cosmic neutrino background, we're reminded that even the smallest, most elusive components of the universe can have a profound impact on its evolution. Shifting our gaze to another enigmatic force, let's explore the phantom dark matter theory and its intriguing implications for the universe's expansion. Unlike ordinary dark matter, which we know exerts a gravitational pull, phantom dark matter is hypothesized to have a repulsive effect. This strange form of matter is thought to behave in ways that defy our conventional understanding of physics, potentially accelerating the universe's expansion at an even faster rate than dark energy. The idea of phantom dark matter arises from observations that suggest the universe's expansion is not just consistent but could be increasing over time. If this theory holds true, it could mean that phantom dark matter is pushing galaxies apart, contributing to the ever-growing vastness of space. What makes this concept even more fascinating is its potential connection to the ultimate fate of the universe. While dark energy hints at a gradual, infinite expansion, phantom dark matter suggests a more dramatic scenario where the repulsive force grows stronger over time. This could lead to a future where the fabric of space-time itself is stretched to its limits. Could phantom dark matter be the hidden force driving the universe toward a fate even more extreme than we've imagined? As we delve deeper into this theory, we're reminded that the cosmos is full of mysteries, each one challenging our understanding of reality and pushing the boundaries of what we think is possible. Now, let us turn our attention to a fascinating theory that seeks to bridge two of the universe's greatest mysteries, the Chaplygin gas model. This concept proposes a unique solution by unifying dark matter and dark energy into a single framework, offering a fresh perspective on the universe's expansion. Unlike traditional models that treat dark matter and dark energy as separate entities, the Chaplygin gas model suggests they could be two manifestations of the same underlying substance. This substance, known as Chaplygin gas, behaves in a peculiar way. In the early universe, it acts like dark matter, clumping together to form the cosmic web that galaxies are built upon. However, as the universe expands, it transitions into a form that mimics dark energy, driving the acceleration of expansion. This dual nature makes the Chaplygin gas model particularly intriguing, as it provides a unified explanation for phenomena that have long puzzled scientists. By combining the effects of dark matter and dark energy, this model simplifies our understanding of the cosmos while still accounting for its observed behavior. The implications of this theory are profound. If Chaplygin gas truly exists, it could mean that the universe's expansion is governed by a single, elegant mechanism rather than two distinct forces. This idea not only challenges our current understanding, but also opens up new avenues for research into the nature of the universe. Could this be the key to unlocking some of the deepest mysteries of space? As we explore the Chaplygin gas model, we're reminded once again that the universe is full of surprises, and every theory brings us one step closer to unraveling its secrets. Now transitioning to an equally captivating idea, we explore the quintessence theory, a dynamic twist on dark energy that could explain the universe's accelerating expansion. Unlike the constant energy density proposed by traditional dark energy models, quintessence suggests that this mysterious force changes over time. Picture it as a cosmic field that evolves, growing stronger or weaker as the universe ages. This variability makes quintessence a fascinating contender in the quest to understand the universe's expansion. One of the key features of quintessence is its potential to interact with matter in subtle ways, influencing the rate of expansion in different eras of the cosmos. This interaction could provide a more nuanced explanation for observations that static dark energy struggles to account for. For instance, quintessence might explain why the universe's expansion seems to have accelerated at different rates throughout its history. The name quintessence itself is a nod to ancient philosophy, where it was considered the fifth element beyond earth, air, fire, and water. In modern cosmology, it represents the fifth force driving the cosmos apart. Scientists are particularly intrigued by the possibility that quintessence could eventually slow down or even reverse the universe's expansion, leading to scenarios like the Big Crunch. However, evidence for this remains speculative, and much about quintessence remains shrouded in mystery. What we do know is that this theory adds another layer of complexity to our understanding of dark energy, challenging us to think beyond fixed parameters. As we delve into the quintessence theory, we're reminded that the universe is not static but dynamic, shaped by forces that continue to evolve. Could quintessence be the key to unlocking the true nature of the universe's expansion? Only time and further research will tell. Now shifting our focus to a mind-bending concept, we turn to the brane world scenario, a theory that suggests our universe might be a three-dimensional membrane or brane floating within a higher dimensional space. Imagine our universe as a sheet of paper existing in a vast multi-dimensional void. According to this idea, the cosmos we observe is just one of many branes, each potentially housing its own universe. These branes could interact with one another, influencing their expansion and behavior in ways we're only beginning to understand. One of the most intriguing aspects of the brane world scenario is its connection to string theory, which proposes the existence of up to 10 or 11 dimensions. In this framework, the extra dimensions could be compactified or tightly curled up, making them invisible to us. However, their effects might still be felt, particularly in how they shape the universe's expansion. For instance, collisions between branes could have sparked events like the Big Bang, triggering the expansion of our universe. This theory also offers a potential explanation for dark energy, suggesting that it could be a result of gravitational forces leaking from neighboring branes into ours. While the brane world scenario is still largely theoretical, it provides a fascinating way to rethink the nature of space, time, and the forces driving the universe's expansion. By considering the possibility of higher dimensions and other branes, we're challenged to expand our understanding far beyond the familiar 3 dimensions of space and 1 of time. Could our universe's endless expansion be tied to the hidden dimensions we cannot yet perceive? The brane world scenario invites us to explore this tantalizing possibility. Now stepping into another intriguing dimension of cosmic exploration, we dive into the holographic dark energy theory, a concept that ties the universe's expansion to the holographic principle. This theory suggests that dark energy, the mysterious force accelerating the universe's expansion, might be deeply connected to the idea that our 3-dimensional reality could be a projection of a 2-dimensional surface. Imagine the universe as a vast, intricate hologram, where all the information about its structure and behavior is encoded on a distant 2-dimensional boundary. According to the holographic dark energy theory, this boundary plays a crucial role in shaping the universe's expansion. It proposes that dark energy arises from the dynamics of this holographic surface, influencing how the cosmos grows and evolves over time. One of the most fascinating aspects of this theory is its ability to reconcile the behavior of dark energy with the holographic principle, which originated in the study of black holes and quantum gravity. By linking the universe's expansion to a lower dimensional framework, the holographic dark energy theory offers a novel perspective on one of the greatest mysteries in cosmology. It challenges us to rethink the very fabric of reality, suggesting that the forces driving the universe's endless growth might be rooted in a hidden, two-dimensional realm. Could the keys to understanding the cosmos lie not in the vastness of space, but in the subtle interplay of dimensions we can barely grasp? The holographic dark energy theory invites us to explore this profound possibility, pushing the boundaries of our understanding even further. Now shifting our gaze to a concept that bends the very notion of time, let's explore the time crystal theory. This groundbreaking idea introduces a new state of matter that defies traditional physics. Unlike ordinary crystals, which have repeating patterns in space, time crystals exhibit patterns that repeat in time. Imagine a structure that oscillates endlessly without any external energy input, a perpetual motion machine of sorts at the quantum level. The implications for the universe's expansion are profound. Some scientists suggest that time crystals could play a role in how the cosmos evolves over vast stretches of time. Their unique properties might influence the rate or nature of expansion, offering a new lens through which to view the universe's endless growth. What's particularly fascinating is that time crystals could provide a bridge between quantum mechanics and cosmology, two fields that often seem at odds. By introducing a dynamic element that operates outside the usual constraints of time, this theory challenges our understanding of how the universe behaves on both the smallest and largest scales. Could time crystals hold the key to unlocking deeper secrets of cosmic expansion? As we continue to probe this idea, it becomes clear that the boundaries of space and time may be far more fluid than we ever imagined. Now delving into the enigmatic realm of black hole cosmology, we're confronted with a theory that flips our understanding of the universe on its head. What if our entire cosmos is expanding inside a black hole? At first glance, this idea might sound like science fiction, but it's rooted in the intricate equations of general relativity. According to this theory, the universe we inhabit could be the interior of a massive black hole, with the singularity at its center acting as the starting point of our cosmic expansion. This concept ties the behavior of black holes' regions of spacetime where gravity is so intense that nothing can escape to the large-scale dynamics of the universe. Some physicists suggest that the Big Bang itself could have been the result of a singularity within a black hole, giving birth to the expanding cosmos we observe today. This idea also opens up the possibility that other universes could exist within separate black holes, creating a vast and interconnected multiverse. What's particularly intriguing is how this theory bridges the gap between the extremes of black hole physics and cosmology, offering a unified framework to explain the universe's expansion. While it raises as many questions as it answers, black hole cosmology challenges us to rethink the very nature of existence. Could our universe be just one spark in an endless fire of cosmic creation? As we ponder this theory, it becomes clear that the mysteries of the cosmos are as boundless as the universe itself. Now shifting our gaze to the simulation hypothesis, we enter a realm where the very fabric of reality might be a meticulously crafted illusion. This theory proposes that our universe, with all its infinite expansion, could be nothing more than an advanced simulation, programmed by an intelligence far beyond our comprehension. Think of it as a cosmic video game where the rules of physics, the speed of light, and the behavior of galaxies are all lines of code in a vast digital construct. Proponents of this idea argue that the universe's expansion could be a deliberate feature of this simulation, designed to mimic the natural processes we observe. One of the most compelling arguments for this hypothesis comes from the mathematical precision of the universe. From the constants of nature to the intricate patterns of quantum mechanics, everything seems to follow an underlying code. Could this precision be evidence of a simulated reality? Some scientists and philosophers even suggest that if a civilization were advanced enough, creating a universe-sized simulation would be within its capabilities. The simulation hypothesis also raises profound questions about free will, consciousness, and the nature of existence. If our universe is a simulation, does that mean our actions are predetermined? Or is there a layer of unpredictability built into the program? While this theory remains speculative, it challenges us to reconsider our understanding of reality itself. As we contemplate the possibility that the universe's expansion might be a programmed feature, we're left to wonder, are we the players, the creators, or simply lines of code in an infinite digital cosmos? As we come to the end of our journey through 30 fascinating theories about the universe's infinite expansion, one thing becomes clear: the cosmos is a place of boundless mystery and endless wonder. From the explosive beginnings of the Big Bang to the speculative realms of the simulation hypothesis, each theory offers a unique lens through which we can attempt to understand the vastness of space. We've explored how cosmic inflation set the stage for expansion, how dark energy accelerates it, and how ideas like the multiverse and holographic principles stretch our imaginations to their limits. Theories like the bouncing universe and phantom energy remind us that the universe's story is far from written, while concepts like black hole cosmology and time crystals challenge us to think beyond the familiar. The incredible diversity of these ideas shows just how creative and curious we are as a species, always striving to uncover the secrets of existence. So, which of these theories resonates with you the most? Do you find yourself drawn to the mathematical precision of the simulation hypothesis, or does the cyclical nature of the bouncing universe capture your imagination? Share your thoughts in the comments below. We'd love to hear your perspective. And if you've enjoyed this deep dive into the mysteries of the cosmos, don't forget to hit that like button, subscribe to our channel, and ring the notification bell so you never miss out on exploring more space mysteries with us. The universe is full of questions waiting to be answered, and we're just getting started. Until next time, keep looking